Okay, so I guess today's topic is again these streaming albums that we had 2 weeks ago. And today we're going to solve this, I guess, I would say slightly more interesting problem than last time, this streaming heavy hitters. So the solution we're going to see, at least towards the end of the lecture today, is going to build on top of these frequency estimation structures we saw last time. Streaming heavy hitters. So like before, right, the data that we see is a stream. So data or the input is like a data stream of pairs, I, comma, delta, and each of these pairs is an update that changes a counter, if you will, or a frequency of some underlying vector or array of frequencies. So it has the effect, it should have the effect of taking the counter for the ith element, should be updated like this. So basically we have this vector of counters that we want to approximate, and so we can add or subtract from one of these counters. Typically we say that these updates are often like some integers, some kind of range, for instance, and this frequency vector, all the frequency recounting elements that come from some universe u. So let's say just the number from 0 to u minus 1. So with this notation, we can think of this frequency vector as it's just a vector of numbers. It's a u-dimensional vector, something like this, right? That's different ways of thinking of it, but basically we're seeing these updates that come in a long stream. Every update changes the value of an entry by adding delta to it. And last time we looked at this frequency estimation, right? So we want to use space that is significantly less than just storing the whole frequency vector explicitly, and we want to use space less than storing all the updates, right? So if the stream length is n and the universe size is u, we want to use space that is much less than u. So we saw last time we saw this. We saw frequency estimation, and we saw a couple of different solutions, right? So one version is that we saw you give it a precision epsilon like this, and then we want to return estimates. I would say f hat of I, such that depending on which setup, which we saw this Misra-Gries, which was the deterministic streaming algorithm that works when we're in the insertion-only setup. So this is like delta is always equal to 1. Saw this just increments. When we saw this solution where, so the way we stated it last time was with a space parameter k, but if we rephrase it, so the estimates we returned were always less than equal to the true estimate, and they were greater than equal to the true estimate minus n over k, where n was the length of the stream. But to make it comparable to the other things we see later today, we could also write this epsilon times the one norm of the frequency vector, and the one norm of the frequency vector is just a sum over I, fi, and put absolute values around it. So it's just the sum of frequencies. We call it n at some point, give a parameter epsilon, which is our precision, and then the space usage of this structure here that do this. Saw last time that it used order 1 over epsilon words of memory. In particular, we could put a parameter k. The way we stated this was that we had a space budget of k counters, and then the accuracy we had was n over k, or the one norm over k here. So if we set k to be 1 over epsilon, we see, so this is what we did last time. And then we also saw these CountMin sketches, the count sketch, when these updates could also be made. So this is a little bit of what we saw last time, but today we want to solve this heavy hitters problem instead. So what do we want to do in this streaming heavy hitters problem? So let's see if I can put it down here. So in the streaming heavy hitters, The goal is instead to heavy hitters. Let's hold in the epsilon heavy hitters. So in this problem, the goal is to output the elements, if you will, the items that occur often. So in particular, here we want to output. Goal is to output a list L. And what we want from this list L, such that what should the list satisfy? So it should satisfy two things. Swap the whiteboards. So the first property we want from this list is that all indices I is such that the frequency of I is at least epsilon times one norm L. So we want to find all the so-called heavy hitters. So the elements whose number of occurrences in the data stream is at least an epsilon fraction of the whole data stream. Makes sense? The ones that make up an epsilon fraction of the weight. So you can say, let's say we initialize it with epsilon being 0.01, then we want all elements that occur at least as in 1% of the data stream. Those are the items we would like to find. And of course, if we only had this requirement, it's easy because then we could just output a list containing all the indices in the universe, because that's definitely containing all the epsilon heavy hitters. So we want also to say something here. The second requirement, this one says no I such that frequency of I, and here I'm gonna say is less than half what it takes to be an epsilon heavy hitter. So what I'm saying is all the epsilon heavy items, the ones that occur in epsilon fraction of the data stream, they must be in the output list. Everyone who is pretty far away from being heavy, so less than epsilon half times the total frequency of the data stream, they should not be in this output list. Okay. And items that lie in between, it's fine if you put them in the output list, it's fine if you don't. Okay. So the reason why we have this gap here is because, as we saw last time, right, if we want to use the sublinear space, we're going to have these approximations, right? So our estimates of frequencies are not exactly, they're not exact. And so I don't think it's too hard to imagine that if we had to distinguish the frequency of epsilon times the one norm from epsilon times the one norm minus one, we were to distinguish these two, we probably have to count exactly. Does that kind of make sense? A little bit. That there should be some gap if we want to hope to do anything. Right? So this is what we allow. We create this region in between where we say, okay, whatever you do in there, it's fine. You are truly heavy, you have to be in the output list. And if you're truly light, if you will, let's say less than half times the one, you're not allowed to be in the output. So this is the goal that we'll aim for. So here, there's really, in this problem, there's really only one query. That is just give me a list of all the heavy hitters. That's the query of this. And the updates are still the same, right? They're these pairs that change the frequency by adding some delta to it. And we're gonna look at it in two different setups today. As a kind of like a warm-up, we're gonna do this cache register insertion only. Insertion only. To this case where increments are always 1. That's what we're going to do first. It's a simple warm-up. And then we're going to do the strict turnstile. If you remember, we can have both negative and positive updates, but we always promise that the frequencies stay non-negative. Of course, there are also solutions for the last general turnstile case. Negative frequencies, they're more complicated, and we're not going to go into those today. I think these other ones are cleaner in this randomization. I would say cleaner and more elegant. I'll stick to those two cases today. These are the ones we do. And I guess as a warm-up, we'll start by doing this this insertion-only setup, just to get started. And for that, we're gonna, I guess, recall this Misra-Gries solution we saw last time. If you remember it, it's Misra-Gries. Gonna recall over here what it was. So we're in the insertion only, right? So we can only increment how many times. So we only get this. We saw one more of element I. So we're gonna write like this. So we have so basically we had this update of I. We saw one more of item I. And remember, Misra-Gries has this base budget of K. Maybe let me write like this. And to begin with, you initialize this set of counters S, that is the empty set to begin with. And then we have these checks. If we have a counter, so let's say I comma C is in S, so there is a counter for I for some C. Then we just update this C by 1. And we also check, oh, well, there wasn't a counter for it, but we're not yet storing K counters. K was our space budget. Then we just add I comma 1 S. Finally, this was the more interesting case. There's no more space, and we're not storing a counter for I. Then we had this procedure where we decrement all counters in S. And then remove any counters that reach 0. Counter reaching 0. This was this Misra-Gries that we saw last time, right? You remember? Then we made some observations, right? We saw that whenever you end in one of the first two cases, your error in your estimate, or maybe we should say, how do we estimate with this procedure? It's very simple. It fits here. So the estimate of I want to know how many times did I appear. Slide like this. So basically, if I comma C is in S, for some counter C, then we return this value C, and else we return 0. This is how we made estimates. Right. And when we analyzed it, also just to recap, we argued that whenever we end in one of these first two cases, we're not gonna make any worse estimates than we did before. And so kind of the difference between any estimate we return on any I and the true frequency will not kind of diverge, so will not be a bigger gap, they will remain the same. Whereas whenever we ended in this last case, the difference between an estimate and the true frequency could grow by 1 at most. Right? And then we argued that this case down here, and we said that this case here, the number of times it can happen is at most n over k plus 1 if n is the length of the string. Remember this? This is what we saw last time. The argument was basically whenever this happens, since all the sum of the counters remain non-negative, whenever this happens, we subtract 1 from k counters, and we were always remaining non-negative. The total number of increments is at most n, so at least this can only happen n over k times. But if we're a little bit more careful, we could also argue n over k plus 1 times. So k operations to count counters up, and then another one to count them down. So in total, k plus 1 operations for this to trigger once. Okay. So question now is, okay, so I guess if we wanted to solve the frequency estimation problem down here, then we just set this k be 1 over epsilon. We got this guarantee here. We even set k plus 1 to equal 1 over epsilon. We're fine. But now we would like to try and solve this heavy hitters problem up there. Actually, we want to, can we use this Misra-Gries solution as it is here to solve this epsilon heavy hitters problem. Maybe with a slightly different K. So this is what we'll try to see if we can do this now. So we want to solve this epsilon heavy hitters problem. So how could we do it? So we want to have an operation now that is like list the heavy hitters. Let's call it that, list heavy hitters. So how could we use this solution? And I'm claiming you can actually use it as it is with the same update operation. Of course, another procedure for producing this list. So how could we solve this epsilon heavy? So maybe try to think for a minute with the one sitting next to you. How could we, from this representation, find all the heavy hitters? Maybe K needs to be chosen slightly different. That's just a hint. So try to think for a minute or two.
This thing here should.
Just a hint here, just in case. This is just a guarantee written formally what we showed last time, right? This is the value of the estimate to do this. Keep going.
Yeah.
Okay, maybe let's see if there are any suggestions. What do we think we can? What do you think we can do? Yeah, maybe an over is set K to no epsilon. That is bigger than necessary. Yeah. You can try to set. Okay, let's try to set to 2 epsilon. Yeah, and then let's set. Let's maybe set K plus 1 to be 2 epsilon. Yeah, and then what do we do when we want to list the heavy hitters? A little louder. Yeah, to what? Yeah, so we look at the counters and then we compare them to what? What do we check? Yeah, we go over all the counters in the ZS, and for each of them we're gonna check something. What are we gonna check? Yeah. If you see something, what do we do? Add I to L. What is the check that we would like to make? Yeah. Yeah. Okay, I guess we forgot to say, let's say we know what the one norm is. We want to check epsilon, or do we want to check something slightly different? Yeah, if we just do this check here, then we might risk, right? So if we are underestimating a little bit, then we might have, if someone was exactly heavy at its frequency of exactly epsilon times the one norm, then we might risk this check fails. So almost, yeah.
Over 2.
Epsilon over 2. Yeah, let's try to do epsilon over 2. Yes. So if its counter looks like its frequency is at least epsilon over 2 times the one norm, then we're going to add it to L. I guess L is initially empty, and then we're just going to return L here at the end. Makes sense? So we're just going to look at all the counters. We're going to see which one of them say at least epsilon half times the one norm, and then we're going to add those i's to the output list. So let's try and check that this is correct, right? So first of all, we have to check that everyone whose frequency is at least epsilon times the one norm will be in the output. So if my frequency is at least epsilon times the one norm, then how big is the estimate going to be if I look at this inequality down here, right? Then the estimate that I would have would be at least, well, epsilon times the one norm minus n over k plus 1. K plus 1 is, this is n over, this is epsilon goes up, 2 goes down. And so this n here is the one norm in this case, in total number of operations, total number of increments. When all these updates, I just add 1 to a counter. So this is epsilon times one norm minus epsilon half times the one norm, epsilon half times the one norm. Right? So what we're saying is, if I had an index I that was heavy, then the estimate I would get by this procedure, and this procedure is just checking what is the counter. This is basically saying the counter for this element I has to be at least epsilon times. This is the argument from last time. So if I had a heavy element, the counter would be at least epsilon half times the one norm. So it will indeed pass this check and be added to the end. So that's good. And then the second thing we have to check is that there's no index I whose frequency was less than epsilon half times the one norm that will be added to the output. But this is easy enough, right? Because the estimate is always less than or equal to the true frequency, right? So in the second case, if it was, so it's less than or equal to the true frequency, and we said that this is less than epsilon half times one norm for one of the light elements. This means it will not pass this check here, right? It will not add any light elements to the output. So indeed, this procedure actually produces a correct output list. That's all the heavy elements and none of the light. And of course, there was this simple thing. Okay, we actually need to know what is this frequency, what is the one norm of this vector f. And I guess that's fairly easy because we know everything is an increment by 1. So I guess we could just kind of have, I guess if we change our update procedure here, I guess we could just have we can just, n is n plus 1. And n is always equal to the one norm. Okay, so this is easy to keep track of, this n. So we just plug in n here and we're fine. So we can keep track of the one norm. Okay. So this is what's fairly easy. I guess the space usage at the end of the day is just 2 over epsilon counters. So we can have a nice space budget of 2 over epsilon counters. And I think you can always convince yourself that this is optimal because, at least up to constant factor, this is an optimal space usage, because how large can this list be? Well, you can have basically if you have 1 over epsilon elements, all with a frequency of, say, 1, let's say your output, if your frequency vector f has some points, there's 1 over epsilon of them, the rest are zeros, then the output list must contain all of those 1 over epsilon elements. And so truly you have to use space proportion to store in 1 over epsilon elements, because they're all heavy. If I have exactly 1 over epsilon elements with a count of 1, then their frequency all make up an epsilon fraction of the 1 norm, right? Because the 1 norm is 1 over epsilon, they're all an epsilon fraction. So actually this is optimal space usage. Good. So this was the, I guess, the easy case of this test register insertion-only setup. And this was again deterministic. You could do it all without randomization. But for this course, I guess what we're really interested in is it's randomized data structure. So now we'll try to move to this strict turnstile setup where we can have negative updates as well. We're just promised that the frequency always stay non-negative. Right? And this is somewhat hard. And here you can prove, if you will, that you need randomization to solve it. So I think here we'll also do a warm-up first, where we try to use one of the data structures from last time, as it is without much modification. But this will give us something that is very slow, and then we'll see how to make it faster. Okay, so you can just erase this not suited. Okay, so let's again remind ourselves what we saw last time for frequency estimation, not in this hash register insertion-only setup, but in the strict turnstile. In the strict turnstile, we saw this CountMin sketch last time. So we're going to build on that. CountMin. So the CountMin structure, it takes two parameters, if you remember, this epsilon and a delta. What does it do? It provides these estimates, and it says, so what do we have? We have the returns. So given an index I, it returns an estimate fi such that the estimates are always overestimates and with probability at least 1 minus delta is not too much bigger than it's supposed to. This was the guarantee that we had last time, right? So it always overestimates, and that's going to be very important today for this solution we're going to see today. And it rarely overestimates by too much. And how did it work? You remember it wasn't too complicated. We constructed a table. The table had 2 over epsilon columns. It had log base 2, 1 over delta rows. It had a hash function for every row. It's a universal hash function mapping keys into positions here. And then it had, I guess, the 2 operations. So it had an update, I comma delta. And this one just looped over the arrays. So let's call this table A, 1 to T. And then it says, this notation, let's say A index J, so the jth row index hash J of I. And here we add, plus let's write like this, we add delta to this row, right? So we hash it in every row, hash an element in every row. This is like whatever. And then we add our delta to those rows, right? So this is hash of I, this is hash 1 of I, hash 2 of I, hash 3 of I. Added here. And also when we wanted to estimate, we want to estimate an I, then we return because they were all overestimates, then we return the minimum over j, jth row, jth hash function applied to I. Like this. This was this CountMin. And then we proved last time that it has this guarantee. So we're gonna build on this today, and we're first gonna do something naive and something that actually has a good space usage. That's not too bad, but it's going to be very slow. Okay, so let's say we don't care about runtime. We just want to produce this list up here, satisfying these two problems. So let's say that's all we want to do. So we want to again do this list, the heavy hitters. And let's say we're allowed to fail now, because in the Misra-Gries solution you could do it without a failure probability. Here you need a failure probability that can do well. So we want to produce this output. Let's say the heavy hitters. Let's say we wanted to fail probability no more than, and just to make the math a little easier. Well, we're just going to say it's allowed to fail probability at most 1 over u size of the universe. Okay. Just to make it, then we don't have to carry around as many parameters. So we would like to give a procedure that can list all the heavy hitters. We're going to store just the CountMin structure with a particular choice of epsilon and delta, and this is what we have to figure out. We want to store one with a particular choice of epsilon and delta, and then we want to use it to list all the heavy hitters. But let's say we don't care about runtime for now. And we want to say, okay, as long as we fail with probability most 1 over u, we're fine. I think maybe try again to spend a minute or two thinking about how could you use the CountMin structure here with some choice of epsilon and delta to produce all the heavy hitters if we don't care about runtime. So maybe that's a hint as well that it's going to be a slow solution. Try to think for a little.
Så visst, stämmer alltså ut. Det är visst viktigt. Ja. Ska du lägga den? Absolut.
Okay, let's see if there are any half-baked solutions or complete solutions are also fine. It's okay if you haven't worked out all the details, but just some suggestion. How do you think how would you approach it? Yeah, ideas. Do something very simple. No guesses. let's see. So we start just by making L just be empty. This okay. So here's the thing. So we're just gonna say we're gonna loop over the whole universe. Okay. We have a CountMin structure that we're querying. Let's call it CM. If CM, let's call it estimate down here. Let's say greater than equal to something, and we're gonna add I to L, and we're gonna return. This is gonna be the pseudocode. So we're gonna loop over the whole universe. So this is of course super slow, right? We're spending U time here, at least. Then we're gonna query a CountMin structure, and I guess we have to say what parameters do we initialize the CountMin structure with. But before that, what do you think would be a good choice to compare with here? Check whether to put it in the output. Yeah.
Epsilon times the 1 norm.
Epsilon times the 1 norm. That makes a lot of sense. Right, so we can already check now that we are going to satisfy the first property here, right? Because, okay, so we have to, everyone who is epsilon heavy, so everyone whose frequency is at least epsilon times the 1 norm has to be in the list. Let's check. So the estimates that CountMin structures are returning are always overestimates, which means that if your frequency is at least epsilon times the 1 norm, your estimate is going to be at least epsilon times the 1 norm. So we at least have all the heavy hitters are in the output list. That makes a lot of sense. Then for the second property, we need to argue that none of the light ones go into the list. Okay. So now I guess we have to be a little careful at how do we initialize our CountMin structure. Maybe let's do it here. CountMin. So what epsilon and what delta do we choose here? So maybe first of all, what epsilon do you think we should choose here? Yeah.
Epsilon over 2.
Epsilon over 2, that's exactly right. So, because if we choose a precision here of epsilon over 2, then we have to look at these light elements now, right? So we're looking at someone whose frequency, the actual frequency is less than epsilon half. Right? So it's one of those. So what we know now, if we choose this epsilon half, then we know for if the frequency is less than epsilon half, then by the guarantee of the CountMin structure, it says then with probability at least 1 minus delta, we haven't set delta yet, but for some delta, the estimate that we're going to get here, where it's less than equal to the true frequency plus, and now we initialize it with epsilon half, right? Epsilon half times the 1 norm. This is less than epsilon half, times the 1 norm. Like this. So these are one of the light elements. So then this is less than epsilon half times the 1 norm plus epsilon half times the 1 norm, so that's epsilon times 1 norm. Right? So what we have now is we choose this epsilon half here as our precision in the CountMin structure that we're building. Then we know with probability 1 minus delta, the estimate that we would get if we tried to estimate a light element, someone whose light would be less than epsilon half, or epsilon times the 1 norm. So it's not going to be put in the list unless we made an error, right? There's a small probability delta that we overestimated by too much, and it will end up in the output list. So now we would like to just choose a delta now, such that this will not happen, right? So what value of delta would make sense now? So we're going to make a lot of these estimations, right? We're going to make U of them. Any one of them might fail with probability delta. We want the final failure probability to be 1 over U. So intuitively, we would like that whatever delta we choose, gonna make u estimations, so we're gonna like this to be less than 1 over u. So maybe if we try to pick delta to be 1 over u squared, right? Let's pick a value of delta of 1 over u squared. Let's try and formally prove that the probability that we add a light element to the output is small. So, okay, when we want to argue that some bad event is unlikely, what do we typically do? Okay, so our bad event is there's at least one light element that was added to the output. So what we do is, I guess we want to define some kind of bad events. Right? So we want some bad events, that kind of failure events. So bad event. What do you think the ith bad event is? What would make sense as an event that we don't want to happen? What could make it break? Like, what could make us add something to the output? Yeah. Yeah, maybe a little similar. So yeah, it's true. It's related to all these questions. Yes, can be stated in terms of these, maybe in terms of these estimates. Say something here. Yeah. So what is it? You know, it's a little easier to state in terms of these estimates. What is it that we don't like? What could cause us to add a light element to the output? Yeah.
The quality of this just
Yes, exactly. If this doesn't hold, so let's write it like this. So this event is that the estimate that we get is bigger than, I guess in this case, epsilon half times the 1 norm. This is something, right? Because if we are to add a light element to L, if I is a light element and it will be added to L, then this event must have happened. And that's the only way it can be added to L. Because if this event doesn't happen, then the estimate is less than epsilon times the 1 norm, and we're not going to add it to the list. So we can only add a light element I to the output if we made a big overestimate of its frequency. Okay. And now we would like to say that not even a single light element is added to the output. So what is this event? The event that we want to found the probability of is the union these events, right? So this is saying at least one element was overestimated by a lot. How can we bound the probability of a union? What is the inequality we have for doing this? Yeah.
isn't it smaller than half probability?
Yes, this is by this union bound, right? So the probability of the union is less than to the sum, and let's just write it out explicitly here. The probability of EI. Okay, what is the probability of EI? By our choice of parameters.
Delta.
Delta, yes, and we chose delta to be 1 over u squared, right? That's how we chose our failure probability. So this is then less than or equal to, each of these terms is 1 over u squared, and they're u terms. So I guess u over u squared, 1 over u. And this is the failure probability that we need. Okay, so this actually, it works. Then maybe we can look at how bad is the space. So what is the space? The CountMin structure here, right? I guess we can look at this one. Space usage for the CountMin is order 1 over epsilon log 1 over delta. Right? This is the size of this table in terms of number of counters. So for us, well, it's order 1 over epsilon half. That's 2 over epsilon. That's still order 1 over epsilon. So this is like 1 over epsilon. And log of 1 over delta, so log of u squared. The 2 also just moves outside the log, right? And becomes a factor 2. So it's actually 1 over epsilon log u. It's a pretty good space use. One can even show that if you're in the strict turnstile where you can both insert and delete, but have non-negative frequencies, this is actually optimal space usage. This can also be proved in a lower bound that this is optimal space usage. So that's great. Then I guess the perhaps not so great thing is the time. Because, okay, so maybe we can also have what is the time for doing one update and one estimate. So the update time is, well, it's just t, which is log 1 over delta. And the estimation time, order. So down here, I guess we have an update time again. Update time is not so bad, right? Because we're just maintaining the CountMin structure. We're not, that's all we're doing. We're just maintaining this CountMin. So the update time is with, again, delta being 1 over u squared. The update time is just order log u. That's good. Now the query time is worse, right? So the time to list all the heavy hitters. So basically we are going to do u estimations that cost log u time each. So the query time is u log u. That's pretty awful. You think if the universe size is like, let's say 64-bit integers, you don't want to do a loop over 2 to the 64 numbers, right, and do work for each. This is bad, and this is what we'll see again after the break. We'll see solutions that improve over this. So let's have a break now for 50 minutes.